the outline of my talk today, first I'm going to tell you a little bit about my deaf sister Victoria, and I'll explain why, and then a little wee bit about me. Then I'll talk a little bit about climate change in general to give the background behind making greenhouse gas measurements and why they're important and why we're motivated to do this. And then I'll say how we measure those gases. And finally, I want to talk for a few minutes about how scientists should engage with the public and media, because the climate change problem is so important in today's world. We can't just live in our ivory tower. We need to talk to the public and the media to get the points across. And throughout the whole talk, I will be talking about the interconnectedness of all things. What do I mean by that? Well, Douglas Adams, who is famous for The Hitchhiker's Guide to the Galaxy, also wrote a book where he talked about the interconnectedness of all things. Now, this might sound a bit silly and humorous, but actually in science, we now talk about interdisciplinary research, which actually is about the interconnectedness of all things. So Douglas Adams was actually in front of all scientists thinking about how important it is to link everything up. Okay, so this Sesquicentennial celebration of Gallaudet University is all about visionary leadership. So that's why I wanted to spend a couple of minutes telling you about my sister, because I believe that she has shown visionary leadership in the deaf and disabled community in New Zealand. As we like to say in New Zealand, where we often like to, the kind of humor we have is to make fun of ourselves, we talk about being world famous in New Zealand. So Victoria Manning did her bachelor's degree in psychology in New Zealand, and then she moved to Gallaudet in 1994 to do a master's degree here. At that point, she knew almost no ASL, and she knew New Zealand Sign Language. So she's already... Yeah. I want to mention her first day here at Gallaudet University. She was amazed. She was walking around all these deaf people that she'd never seen so many deaf people before, all signing away. But then after a while, she got a bit thirsty, and she wanted to ask for some water, and she didn't know where to find some water. But she had this, she only knew New Zealand Sign Language with a few American signs. So this is what she signed. I'm thirsty. In New Zealand Sign Language, the sign for water is like this. So she was this young, very pretty young woman asking these young men for some sex. I'm not sure what happened next. I didn't ask. Anyway, a couple of years later, she finished a degree at Gallaudet University in mental health counselling, and she returned to New Zealand as the New Zealand's only mental health counsellor for deaf people. Something where she really showed visionary leadership, where she had a 5-year battle with Telecom New Zealand to get a free phone relay service for deaf people in New Zealand. She was inspired by having lived in the US for a couple of years and seeing how you have it here, and she fought Telecom, which is New Zealand's largest company, for 5 long years, and she eventually won this battle, and they gave the deaf people of New Zealand a free relay service in 2002. She worked in the government for the Ministry for Social Development, Office for Disability Issues for many years. And then in 2006, New Zealand Sign Language became an official language of New Zealand. We're the only country in the world where sign language is actually represented by the government as an official language. And again, Victoria was very instrumental, along with many other deaf people, in making that happen, because she was the key government advisor pushing that along. Again, that took several years of work and, I would say, visionary leadership. And then for the last 5 years, she's been working for the Human Rights Commission in New Zealand. She got a bit frustrated in the government, actually, and she found if she moved out of the government, she could actually make more happen. The one other thing that she does is, together with her hearing husband, Paul Paul is a film producer, and so they make various documentaries and films. They made one called Sign of the Times, which is a documentary about the whole process of New Zealand Sign Language becoming official. And they've also produced a Sign with Your Baby DVD for deaf and hearing parents of deaf children in New Zealand. So she's really done a lot of stuff, and I'm extremely proud of her, which is why I wanted to take this opportunity to tell you a little bit about her, since she's a Gallaudet alumni. Okay, so what about me? Well, I'm a Kiwi. I'm from New Zealand. This is a real Kiwi here. It's a bird, but we call ourselves Kiwis too. I come from Wellington, which is in the bottom of the North Island there. New Zealand looks like this tiny wee country here, but actually it's a very long country, and it's equivalent from traveling from South Carolina to Nova Scotia, Canada. So it actually covers a lot of area. It's also the home of Middle-earth, Lord of the Rings, and The Hobbit. We're all filmed in New Zealand and produced in New Zealand, and we're very proud of that fact. The bottom picture is a view from the house where I spent my life growing up. And as with all Kiwis, I'm a big fan of rugby. We won the last Rugby World Cup, which was held in 2011. And this is a sport, unlike your American football, this is a sport for real men because we don't wear any padding. This is a slide that I show my students. Most of my students at university have never even met a deaf person. So in the very first day, I tell them that I'm deaf, that I have a cochlear implant, and then but I don't want to make it into a serious, awkward thing, so I have a couple of jokes that I show them as well. Perhaps I'll just read them out here. The one on the right says, it's a joker with the bells on his ears, and it says, "You've got a ringing in your ears." And the middle one is from the far side. "Those snakes, oh, they're just signing, honey." And the one on the left-hand side says, "No, you deaf old goat. I said, show me your pass." If you remove the letter P, you'll see what he thought he said. This month at Gallaudet, you have a visionary leader for each month, and this month's leader is Glenn Anderson, who was the first deaf African-American to get a PhD in the USA. So that's kind of a nice synergy to myself being here, because without trying to sound too arrogant, I'm actually the first person in New Zealand to have got a PhD. So it's a little bit of a connection with Glenn Anderson, perhaps. I think today I want to, as you all know, there are very many different meanings of the word deaf. The one that you identify most is deaf with a capital D, referring to deaf culture and identity. I want to talk about two meanings of the word deaf for myself. The first is that I grew up as a deaf person in the hearing world, and I felt very isolated because I didn't fit into either the hearing world or the deaf world. So that's the first meaning that's important to me in my everyday life. The second meaning of deaf, which also hits me on a daily basis, is how most of the world I find are deaf towards the problems of climate change. And that's the meaning of deaf which I want to spend the rest of today's lecture talking about. So first, a little bit about climate change in general. We live in interesting times. Terry Pratchett, who's England's most famous fantasy author, wrote a book called Interesting Times. He used it as a euphemism for civil war. I use it for a euphemism for right now we are pushing the Earth into a state that's never been seen before. Yes, climate has changed in the past, as the Republicans here like to tell you, but it's never changed as rapidly as it is today. And also, when it changed in the past, it was certainly in a condition that would not be pleasant for humans to live in. So this slide here is showing the temperature record from the last 150 years. And it shows a clear upward trend. Now, another thing that you hear from skeptics is that, oh, the temperature is not as hot as it was in 1998, which was a very hot year for reasons that we understand that were not actually related to global warming. There's a lot of variability in the climate system, which is why in the bottom half of the graph here, what it's showing is the decadal averages, the average temperature for every 10 years, because it removes that year-to-year variability, which makes it so hard for us to see what's happening in the long term. If you average over a longer time period, it becomes very clear what is happening. There's another important thing. Most of what we hear about the land temperature, but actually most of the extra heat is going into the oceans, shown in this slide. More than 90% of the heat is going into the oceans, and we're not measuring the ocean temperature very much. All we seem to think about or care about is the temperature on land. So even if we get a colder year on land, the oceans were still getting warmer, and we don't read about that or hear about that. So it's important to keep that in mind when some people might be telling you that climate change isn't real. The heat is going somewhere else. It doesn't mean it's not there. And just to show it in a different form again, the top plot is now showing the whole world for the increasing temperature in the last 100 years. And you see that some places are getting warmer faster than others. It's different wherever you go. And in the bottom plot, we're now doing something different, where we're trying to predict the future temperature. It goes to the year 2100. But of course, prediction is a very difficult thing to do. So what scientists have done is they've come up with several different possible scenarios. There are 4 shown on the right-hand side there. The dark blue, pale blue, and 2 orange ones. Depending on what humans do, we might follow one scenario or the other. And you can see the increased warming to the year 2100. If we take the best scenario, it's less than 2 degrees. But unfortunately, we really don't seem to be following that scenario. We seem to be following this top one here, which is going to take us to more than 4 degrees of warming by the year 2100. It's not just about temperature. That's what this slide here is showing. There's many other effects of climate change, almost all of them negative. All of these slides are showing 100 years from 1900 to 2000. The one on the top right here is showing the increasing ocean temperature. The bottom one here is showing sea level rise, which is most of the world live within a mile or so of the coast. So if the sea level is rising, this is a big problem for us. And then the other one you hear about in the news is the Arctic sea ice is decreasing year on year. And that's shown in the bottom left here. So it's not just about temperature. There's many effects of climate change, most of them which are causing problems and will continue to cause bigger problems in the future. Okay, so here's a little break for a joke talking about sea level rise. The sharks are saying, good news. At the current rate of global warming, we should be able to just swim over there and eat him in under 5 years. Another thing that's happening is the glaciers are receding in most parts of the world. Now, here I'd like to make, the obvious point is the glaciers are receding, but I want to make a second point with this slide. It's very easy for both scientists and climate skeptics to find some picture to sort of shock you, to show them to give the point they want to give. So this is not a scientific thing to do, to show a photo like this. What I should be showing you is the next slide. This shows almost all the glaciers in the whole world, whether they're growing or decreasing. And we can see that the blue ones are showing glaciers that are actually getting bigger, and there's 1 or 2 of those. So there are some glaciers that are getting bigger in a few parts of the world. But by far the majority of the glaciers are receding and getting smaller because of global warming. So again, I make the point that this picture, yes, it can say something, but it's only showing 3 glaciers in the whole world. You could easily pick it's called cherry picking, to pick and choose the things you want to make the point you want. It's better to be more statistical and show as much data as you can, such as this plot here. Another very important thing with respect to climate skeptics is that 10 or 20 years ago, climate skeptics said the climate's not warming. They've given up on that argument now because it's pretty obvious it is warming. So now they say, yes, it's warming, but A, it's always warmed, which I mentioned before, and B, it's not caused by humans, it's just natural. So this slide here is proving that that's not true. What we've got here is slides from 100 years from 1910 to 2010, and the black line is the observed temperature change on the left-hand side on land, on the right-hand side increasing ocean temperature, and in the middle land and ocean combined. Okay, so the black is the observations. What the blue shading shows is some model predictions of temperature, and the blue one is when we only use natural events which predict the temperature, okay? And we see the blue is not following the observations. The pink is showing some different models, well, the same models, but with additional parameters put in them, where we have the human forcings, such as greenhouse gas increases. When we add the greenhouse gases to the model, then all of a sudden, the models are showing the same effect as the observations. So this slide very clearly shows that it's not natural events which are causing climate change. And the other argument the skeptics use is, okay, yeah, it is getting warmer after all. We were wrong. They never say we were wrong 10 years ago, but they should. And then they might say, okay, it's not natural, it's happening by people. Then they say, but it's a good thing. It's too cold here. I want it to be warmer. I can go on the beach more often. Climate change is not a good thing. This is not my area of expertise, so I just have one single slide about it. I just very quickly touch on this in this slide here. A very small amount of warming can be good for some areas, yes. But we've already passed that threshold. It's already about 1 degree warmer than it used to be. We're getting lots more extreme weather events. As you know, here in Washington, D.C., it's been extremely cold. Being extremely cold is not a contradiction to global warming, which is why we try to use the phrase climate change as opposed to global warming. But climate is changing. Sometimes, in the long term, it's getting warmer, but there are always extreme events, such as the cold you've been experiencing here in D.C. In Australia, it's been extremely hot this summer. They had to shut down the Australian Tennis Open because it was too hot. The tennis players were in danger of dying if they carried on playing tennis, so they actually stopped it. This was just last month. It was extremely cold in Europe last year. In England this year, they've had extreme flooding all over the country. We talk about once in 100-year events. Well, they seem to be happening at least once every 10 years now. Okay, so all these extreme events are happening much more often, and this is the indicator that climate is changing very rapidly. As the planet gets warmer, it will destroy all kinds of biodiversity in the world. It will destroy natural ecosystems, and it will destroy coral reefs. One interesting side story, if I can mention, is this is actually happening on the east coast of the US. You've got these these birds called warblers, which migrate south every year, and they migrate north in the winter, in the summer. They're not migrating as far as they used to migrate because the temperature's warmer. Okay. Now those birds, they eat worms in the forest. The worms obviously cannot migrate. So what's happening is the birds are coming back in the summer, and they're not flying as far south anymore. They're going to a different place, leaving behind the worms in the trees, and the trees are destroying the forest. The worms are destroying the forest, okay, because they've got nothing to control the worm population anymore. So here on the East Coast, you've got a lot of forests dying because the worm population is exploding and not being controlled by the birds because the birds aren't coming back to where they were before. This is one example of natural ecosystems changing because climate's changing in a way which we didn't predict, okay, and in a way which is very negative. Okay, so I hope I persuaded you that climate change is an important topic to study and to know more about. So my next topic is, why should we bother measuring greenhouse gases? The simple answer is because it is greenhouse gases which are causing all the climate change on Earth today. And so that's what I'm going to talk about in more detail. So two key questions that climate scientists ask themselves. First of all, how hot is it going to get? And second of all, how much fossil fuels can we burn safely to keep total warming below 2 degrees, for example, or some other acceptable value. How hot the world's going to get is basically a human decision. I'm showing again the same graph as before. It's a human decision which of these tracks to follow. But how much can we burn is a question about the carbon cycle. We do not understand how the Earth is responding to the changes we are making. So in each of these scenarios, you've got a solid red line, and you have a range of possible temperature. That range shows what we don't understand. We can't just draw a line because we don't know what's going to happen exactly. So whether you go on the blue line or the red line depends on a human decision, but where you are in the range of each line depends on how the Earth responds to our actions, and we are not sure at the moment because the carbon cycle is extremely complicated and it needs more study. We don't understand it well enough yet. That's the bottom line, which is why people like me are trying to understand better so that we can give better answers to the politicians about what will happen. Okay, so let's start thinking about understanding greenhouse gases more. This slide here is showing, if you look at the red one in the middle first of all, there's a carbon dioxide concentration in the atmosphere going back 600,000 years. How do we do that? How do we measure the air so long ago? We go down to Antarctica and we collect ice, and what we see here is lots of air bubbles. Those bubbles of air are hundreds of thousands of years old, trapped in the ice. We retrieve that ice and we take out the air and we measure the CO2 concentration in the air to find out what the concentration was long, long ago. And then we come up with this graph here. And what we see is that it varied between about 180 ppm and 280 ppm. So ppm means parts per million. That means that there is 180 parts of CO2 for every 1 million parts of air. So yes, it's very small, but still it's very potent and important. So in 600,000 years, it went up and down like this. This was mostly caused by glacial and interglacial cycles. And today, we're up here, okay? So it's shot way up here. And actually, this graph is already about 10 years old because this says 370 ppm. We're already above at 400 ppm now. The blue line is showing the same thing for methane, okay? Methane is the second most important greenhouse gas after CO2. And again, we see the same thing. It was oscillating for 600,000 years around these numbers here, and now it's more than doubled all the way up to almost 1,800 ppb. Nitrous oxide, N2O, is the third most important greenhouse gas, and again, it's oscillated around here, and now it's at a higher level than we've seen for more than 600,000 years. So in other words, the Earth is in a state it has not been in for almost 1 million years. These are greenhouse gases which are warming the Earth. Okay, so we need to understand the behavior of CO2 better. CO2 is the most important greenhouse gas for causing warming and climate change. We emit CO2 when we burn fossil fuels. There are three kinds of fossil fuels: coal, oil, and natural gas. Natural gas is just methane. Okay? When we burn these for our energy needs, driving your car or warming your house, you produce CO2 and it goes into the atmosphere. The amount that we're burning is enough to increase the atmospheric concentration by 5 ppm every year. So remember, the amount we have right now is about 400, so we're burning enough fossil fuels to increase it by 5 every single year. But we are extremely lucky because the oceans and forests of the world are absorbing half of the CO2 that we emit, slowing down climate change and global warming by a factor of 2. Okay? So this makes us very lucky. It reduces the impact on climate by half. But the big question is, will the oceans and forests continue to give us a free ticket? And the answer is we don't know. We don't understand the carbon system well enough yet because it's simply too complicated. The graphs I'm showing here, on the left-hand side, these are from model data now, into the future to the year 2100, and we've got 15 different models predicting on the left-hand side how much the forests will take up in the future, and on the right-hand side how much the oceans will take up. From 15 different models, look how different they are. This shows that we just don't know what's going to happen. In the case of the land, sometimes, okay, if we've got a positive number here above 0, that means the forests are taking up CO2. When the number goes negative, the forests are actually giving off CO2. So we see that in the future, in the year 2100, some of the forests start giving off CO2, depending which model you believe. Other forests show it taking up CO2. In the case of the oceans, all the models show continued taking up CO2, but with quite very different numbers, a factor of 2 different. It's because we don't understand this well enough that we need to keep studying, because we talk about 2 degrees warming being dangerous, but how much CO2 can we emit from the fossil fuels which will allow only 2 degrees of warming? The truth is we're not really very sure. We can give you a rough number, but we might be wrong simply because the carbon cycle is so complicated. Okay, so now moving more into my kind of research, which is measuring CO2 in the atmosphere. Okay, so I've given you the motivation why we need to make these measurements. So what about those measurements then? So as Carrie helpfully explained to you, Dave Keeling started measurements in Mauna Loa in 1958 of carbon dioxide concentration. And he continued this until he died in 2005 when his son carried on. So it's still going on today. Not so well known is he actually started measurements at the South Pole before Mauna Loa in 1957. And that's the blue line shown here. Now, the first thing you notice is the blue line's going up too, even though the South Pole is very clean air, but it doesn't have a big cycle like the green one, okay? The blue one's quite flat and the green one's up and down. So what does this tell us? Well, when Dave Keeling first made these measurements, I'm zooming in now on the first couple of years. He started off making measurements here and CO2 was going up and he was happy. That's what he expected. Then you see there's a gap here, and that's because his instrument, there was a power cut and everything went down. He had to fly back to Hawaii and turn it on again. And when he turned it on again, CO2 had gone down. He thought something was broken. He didn't understand what was going on. It kept going down and down and down. Then there was another power cut. After that power cut, CO2 went up again, and he was happy again. CO2 should be going up, right? But then it started going down again. Somewhere about this time, Dave Keeling realized this is not just about a broken instrument, something else is going on. And what he realized is that this up and down of CO2 in Mauna Loa was caused by the forests of the northern hemisphere breathing. When forests are growing in the summertime, they take up CO2, and in the wintertime, when all the leaves die, they give off CO2. This changes every single year. We understood this, and we know that changes the atmosphere. What was unexpected was this is Mauna Loa, which is a tiny island in the middle of the Pacific Ocean, and they could see the forests in Hawaii. So in other words, the air mixes very fast in the northern hemisphere. We didn't know that back in that time. So it's an example where we learned something else about the Earth without even intending to by making measurements in the atmosphere. And so that's why I'm very excited about that, because I make measurements in the atmosphere, and it's cool when we learn different things. Okay, Cinderella was in my title, so I've got to explain what Cinderella's about. This is actually a Nature article from 2007 where Nature talked about Cinderella science. They talked about our work by Dave Keeling being Cinderella science. It's unglamorous work seldom rewarded by funding agencies or the science community, but we neglect it at our peril. This work's kind of cool and fun, but it's hard to convince funding agencies of that. They don't see the point in making measurements for the long term. They just want quick results. And another article in The Economist said the same thing. In The Economist, they wrote, "You might think that measuring the levels of greenhouse gas in the atmosphere will be a priority. If you did think that, you would be wrong." Okay, let's get back to the atmosphere and the science. So then Ralph Keeling came along 30 years later, and he started making oxygen measurements, and also at Mauna Loa, and he found that oxygen was decreasing, and it's decreasing even faster than CO2 is increasing. He also made measurements in the South Pole and found the same thing. Now, when I teach this in my class, I spend a whole hour just talking about this slide. I obviously don't have that time now, so I'm going to rush across more quickly and say, okay, if oxygen keeps decreasing like that, then this could be bad for us because we need oxygen for breathing. So humanity's last gasp is going to happen if we keep burning fossil fuels. Luckily, there's two reasons why this is not a problem. First of all, okay, well, the world is doomed. It's not true. First of all, the time scale. Here we are in 2014. It would take 50,000 years before this would happen. So it's not an immediate problem. But even more importantly, we will use up all the fossil fuels long before oxygen can decrease by anything that's significant. It will never drop below 20%, so we don't have to worry about the decrease in oxygen from a human health point of view. As a scientist, it's important to be very open to different possibilities to explain your work. So I did a literature search to look for other reasons why oxygen might be decreasing in the atmosphere. And during my literature search, this is what I found. Calvin and Hobbes. And Calvin asked his dad, why does the sky turn red as the sun sets? And his father said, that's all the oxygen in the atmosphere catching fire. Okay, I want to explain to you why oxygen is decreasing now. At the same time, CO2 is going up. So I've got an explanation here, a simple sort of schematic of the whole world. On the left-hand side, we've got photosynthesis from the forest, and all of these blue arrows are carbon dioxide. Okay, so when the forest is photosynthesizing, it's taking up CO2. In the wintertime, it's respiring, and it gives CO2 back off into the atmosphere. At the same time, we are burning fossil fuels, which put CO2 in the atmosphere. And we've also got exchange of CO2 between the air and the water in the oceans, constantly exchanging in both directions. Okay. Now, the net effect is, at the moment, the forests of the world are growing. Despite deforestation, forests over the whole world are bigger than they were last year and bigger than the year before. Because the forests are growing, that means we've got more photosynthesis and respiration. So the net effect is that CO2 is coming out of the atmosphere and into the forest. The net effect from fossil fuels, of course, is CO2 into the atmosphere. The net effect from the oceans is that the oceans are absorbing CO2. As you might know, if you've ever had a glass of Coke, CO2 is soluble in water. Okay? And so as we put more CO2 in the atmosphere, that CO2 will dissolve into the water. Okay, so the oceans are taking up CO2 simply because CO2 dissolves in the water. Now let's add oxygen to this picture. So oxygen is shown by the green arrows, and in most places it's doing the opposite thing. When the trees are growing and photosynthesizing, they're giving off oxygen. When they're respiring, they're taking up oxygen. When we burn fossil fuels, we consume oxygen. And so we have a net effect of oxygen in the opposite direction from CO2. But in the water, there's no effect. In the seawater, there's no effect from oxygen because oxygen is very insoluble in seawater. CO2 is very soluble, oxygen is not. Okay? So there's no effect of oxygen in the water. So what that means, I don't want to go into too much complication here, but on the bottom left here, we've got a global budget for CO2 and oxygen. And I guess to put it simply, if we measure CO2 and oxygen in the atmosphere, we can calculate how much CO2 is going into the oceans and how much into the forests. If we're only measuring CO2, we can measure CO2 in the atmosphere, we know how much fossil fuels we're emitting, but we don't know how much goes into the ocean and how much into the forest. If we measure oxygen as well, we can answer these questions and say exactly how much CO2 is going into each of these two places. And that was the motivation for making oxygen measurements. Okay, we're not worried about oxygen decreasing because it's not going to decrease much. We want to know where is the carbon dioxide going, how much is going into the land, into the forest, and how much into the ocean. Oxygen measurements can answer that question. How am I doing for time? I'll skip ahead a little wee bit. So in this slide here, I want to summarize what we've learned from measuring greenhouse gases. We have pushed the Earth to a state that hasn't been seen for at least 600,000 years. Atmospheric CO2 and oxygen measurements can quantify the ocean and land carbon sinks, which are slowing down climate change, and they're very beneficial to us. We can examine if climate feedbacks are modifying this carbon sink by running computer models. And we've been able to, the slide I didn't show you, we've been able to show that the northern hemisphere carbon sink is not as big as we thought. It turns out that more of that carbon sink is in the tropics and the Amazon than we realized before. And we figured that out by making measurements in the atmosphere, not by measuring in the forest and the Amazon. We can also calculate, the very big political question now is which forests of the world are taking up CO2? Is it the forests of North America and Canada? Is it Europe? Is it Siberia? We're not quite sure, but we're starting to be able to answer those questions by making more atmospheric measurements in those different places. Okay, so now just very quickly a few slides about how we actually make these measurements to give you a bit of appreciation for the work that I do in my lab. And the first thing to let you know is that making oxygen measurements is really, really hard, and not many people do it. If you want to measure CO2, remember the CO2 concentration is 400 ppm. We'd like to measure it to a precision of about 0.1. And so to do that, it's about 0.03% precision. If we want to measure oxygen, which is in a background of 21% to the same precision, it's much, much harder, okay, shown by this number here. So you could say it's actually 630 times harder to measure oxygen than it is to measure CO2, if you just take this number here. It's not as simple as that, of course, and it's actually not that much harder. I would say it's about 100 times harder to measure oxygen. That's why it took longer before we started doing it. So this is a photo of my lab in England. It's called the CRAM lab, which stands for Carbon-Related Atmospheric Measurements. But as you also notice, it's very crammed with a lot of equipment in a very small space. We like to give names to our equipment, yeah, they're called different names. This is a vacuum ultraviolet oxygen analyzer which makes the oxygen measurements. And we had to calibrate our analyzer with calibration gases. This is what we call the blue box, which has lots of calibration gases. And this is where we make those calibration gases, because you cannot buy them from any commercial company. Industrial companies don't make these gases. And now I want to mention the GOLEM program. As I mentioned, I'm a Kiwi from Middle-earth, but GOLEM actually stands for Global Oxygen Laboratories Link Ultra-Precise Measurements. Let me move ahead to this slide. If we're measuring in England, this is where I live, and we measure the carbon dioxide concentration, and if my colleagues in Germany measure a lower carbon dioxide concentration, what that means is as the air moved across Europe, the CO2 has been sucked up by the forests, okay? But what if the German measurement was different from my measurement? Then I would make the wrong assumption that the forests were sucking up CO2, and actually maybe it was not a bad measurement, but a different measurement. Okay, this is what the GOLEM program fixes. What we do is we have some bottles filled with air, and we send them around every lab in the world, and every lab measures those bottles and to see if we get the same number. And that gives us confidence when we measure something, a difference like this between England and Germany, that that number is real. Okay, so that's what the Golem program is all about. Okay, so my last topic is how should we scientists engage with the public and media? Well, I like to think, well, I don't like to think. Unfortunately, a lot of politicians are like ostriches with their head in the sand. Okay? Here's your politicians in Washington, D.C. I don't know if I really recommend this movie called The Insider. It's quite an old movie now with Al Pacino and Russell Crowe. It's all about the tobacco industry. About 40 or 50 years ago, when Russell Crowe plays a scientist who discovered that nicotine was addictive. Well, he was almost killed by the tobacco industry. They put pressure on him. He lost his family. So the tobacco industry is so powerful that they try to shut him up, basically. It's similar right now with climate change. We've got the oil industry trying to tell us that it's not happening. They're putting pressure on the governments. They're giving all this money to the politicians to not believe in climate change. So I see it as a very strong analogy with the tobacco industry 40 years ago with climate change today. So I recommend the movie from that point of view. I see this as a fight in the gunfight in the OK Corral, okay, with Wyatt Earp. This is a serious problem. Some people call this a more serious problem than terrorism. Wars are going to happen because of climate change. Countries are going to lose their water source, their food crops. People are going to start fighting wars. There's one group of Americans that do believe in climate change. That's the Pentagon. Forget about the politicians. The Pentagon know that climate change is a real threat to American security, okay? So we had to convince the rest of the world. Now, the next thing is many scientists, we're bad communicators, unfortunately. Back in 2010, there was a lot of publicity about climate change, and there was this article in the New York Times. It was written by Al Gore. It was by far the best news article I read about climate change in a whole year. There's no coincidence that this was written by Al Gore. He's a politician. He knows how to communicate, whereas scientists, unfortunately, do not. So this is what we need to fix. We had to teach scientists how to communicate to the public and to the policymakers to make change. If the public believe in climate change, they will put pressure on their politicians, and the politicians will have to take action, or else they will lose their job. Another Terry Pratchett book was called The Truth. This book was all about the invention of the printing press. And what happened in this book is that it just transformed the world, because all of a sudden everybody had news. The newspaper was delivered to people's houses, and the information from the average person went up dramatically. We're having the same transformation in today's world with social media, with Facebook and Twitter. Information is at our fingertips in a way that it never was before. This changes how fast the world can act, and we had to take advantage of this in the climate change problem. Another thing that we need to do is we need to educate our children. The children are tomorrow's voters. So there's a couple of efforts in Europe to do this. There's something called Cabo Schools, which is a partnership between climate researchers and secondary school teachers. There's another organization called the Teacher Scientist Network. Unfortunately, these are small organizations. Most of us scientists say, oh yeah, I'd love to do it, but I don't have time. I'm in exactly that category, sadly. We need to make time for this. It's so important to educate the children. Another example of something I've been working on is a project called CO Tomorrow. I worked with a couple of artists, actually an American from Los Angeles, and we developed this light sculpture. This is at the Royal Academy of Arts in London, and the lights here were changing based on the carbon dioxide concentration at my station in England. So it's just sort of gimmicky kind of thing, but it's an example of just telling the public about our work in a way that's sort of interesting to them with some colored lights and stuff like that. So we need more stuff like this. So what I would like to do next, as a development of CO Tomorrow, is you've probably all heard of the London Eye in England. People line up here for 1 hour waiting to get on the London Eye with nothing to do. What if we put some CO2 displays here with monitoring CO2 at London Eye and some information stuff, just telling them about it? You've got hundreds of thousands of people coming to this demonstration. This would be a cool thing to do to engage and communicate with the public. Unfortunately, I can't get funding to do it. Okay, and last of all, the United Nations have what they call goodwill ambassadors. The strange thing about humans is that we listen to our celebrities, despite the fact that they're typically not educated in science or whatever. We listen to them. Angelina Jolie and Roger Federer are two United Nations goodwill ambassadors. The United Nations understands that humans listen to our celebrities. So my idea is climate change ambassadors, because we listen to these guys, right? And the first celebrity I had in mind was a guy called Jonah Lomu, who's the world's most famous rugby player. He's now retired. He's actually a good public speaker. But here in America, you might not listen to this guy because for you, he's not a celebrity. So the idea I had was Peyton Manning. I had this idea before Sunday. But now he might be looking for a new job, so maybe he could be a climate change ambassador. Thank you very much.
Hello, I'd like to introduce myself. My name is Keith Doan. I'll be graduating this May. And I'm leading the green programs here at Gallaudet. I'd like to open the opportunity for questions and answers now. Hello there. I was just watching the Super Bowl and I saw one of the commercials there. Oh, sorry, not everybody could see me. So the Exxon commercial during the Super Bowl, they were talking about carbon concentrations being, talking about 60% reduction in that. And I was wondering if that advertisement is true to life. Well, I'm not sure where in the world they were measuring. I think it was here in America. Yeah, I was pretty suspicious when I saw it. That's why I thought I'd ask. I'd also like to ask a second question. I was reading one article that said 100 years from now, many of the animals that currently exist will be extinct because of climate change.
That's true. That's a biodiversity problem, especially in the Amazon, because we're destroying the forest. But also, as the temperatures warm up, coral reefs might be extinct in 100 years. There may be no coral reefs. In Australia, the Great Barrier Reef, which is the world's most famous coral reef, is going to die even faster because last week the Australian government gave permission for a coal company to dump their, when they're searching for coal, they've got all this leftover trash, and they can dump it now on the Great Barrier Reef, so it's going to die even faster. And it's a coal company, and the Australian government has approved this. The Australian government's actually right now basically it's worse than your government in terms of climate change. So yeah, it's not my specialty, but I think biodiversity loss is very important. One more thing on that topic is that medicine research is a huge research area. We're trying to find cures for cancer and all this stuff. And we think the answers are probably in the forests of the world. There are chemicals in trees and plants that we've never heard of or never discovered. And many of the things we have discovered have come from there. But if we're killing off all this biodiversity, we're not even going to find the cure for cancer in these forests anymore because they'll be gone.
Wow. That's horrid. But thank you very much. Thank you. Other questions? Thank you very much for your presentation. I enjoyed it. My name's Derek, and I was a student here. Now I've graduated and am working here at Gallaudet. So in looking at your presentation, I found it fascinating. But I wanted to ask, what can we here at Gallaudet do? Can we, what model can we adopt to really encourage more environmental friendly practices and especially with our budgeting practices. And I believe that the community together can do something greater. What suggestions would you have for us as a community?
I think maybe there's a couple of answers to that. The first is what I try to practice is to lead by example. So try to have an environmentally friendly life just in your own day-to-day life. Yes, it's only a drop in the ocean and a small influence, but if you're leading by example, that can help. Secondly, so by lead by example, I mean, try not to drive a big car, and if you can afford it, get some solar panels on your house, things like this. I mean, whatever is practical and reasonable for you. Secondly is you're in Washington, D.C. here, where all the politicians are. So I don't know if it is easier here to talk to your politicians, because if it is, they're the ones who can make the difference. But then, of course, it's also about, as I mentioned, just communication to the public. And if you're just chatting with somebody at a party on Friday night and they say they don't believe in climate change, if you know something about it, then say, well, that's rubbish, and explain why to them why it's rubbish, if you have some knowledge yourself from my presentation or from some reading or something like that. It's just about spreading the word, I think.
Thank you. Hello there, I'm Mike. And I'm taking a class right now where my project is to look at the environment and see how we can reduce CO2 and look at the different models. So in my research for the class, I found that the North Pole does seem to be shrinking in some of that, but what about the South Pole and Antarctica? Are we starting to see shrinking glaciation there? And is that really sort of the alarm bell of the world, as I've read? What can we do about the South Pole and keeping the ice melt at bay?
It's a very complicated question, and I'm not the person who knows much about it, so I can only say a little bit. Perhaps the most important thing with respect to the water cycle is that as the temperature is warming up, the oceans are evaporating more water. So there's more water in the atmosphere. That means we get more precipitation, we get more rain and more snow, which we've been seeing in some places. Some places are flooding, and you're getting more snowfall in some places. So there's just more water sitting there, but that also means that in some parts of the world, the glaciers might be getting bigger because there's more snow. Okay, that doesn't mean global warming is not happening. It just means there's more water and therefore more snow. So that's one point. So just because a glacier is getting bigger doesn't mean global warming is not true. A second point about ice in Antarctica is that a lot of it is it's floating, it's not on the continent. If floating ice melts, it does not change sea level. Maybe you know that. So floating ice, actually you can just take an ice cube if you take ice in a glass of water, when it melts, the water level doesn't change. Okay, so floating ice melting is not a problem. What's a problem is the ice on the continent of the South Pole and also in Greenland. The ice melting in the Arctic is not a problem for sea level rise, it's a problem for other things. Am I answering your question?
Sort of. So I have found that sea ice melting doesn't really affect sea level, but the falling ice off of glaciers coming into the ocean does have more of an effect on sea level rise. But what kind of ideas? Could there be sort of land levees to prevent that from happening? Barriers that would prevent that land ice from affecting sea level? What kinds of things there can we do?
You mean trying to prevent the ice from breaking away? Is that what you mean?
I'm saying that since to prevent the sea ice or the ice on land from going into the ocean, is there some way to prevent that from happening? So we see some of the ice and glaciation on land melting, going into the oceans. That creates rise in sea level. Is there any way to keep that land ice from going into the ocean?
I don't think so. I think the way I appreciated that is I have flown to Antarctica one time, and you get to appreciate just how big of a scale we're talking about. It's hundreds and hundreds of miles of just ice. I mean, we don't have the engineering technology to build something on that sort of scale. It's too big.
Okay. Okay, thank you. Hello, thank you for coming. I have 2 questions. So I was wondering about your science team and its connection to government support and whether or not you work directly for the government. And I was also wondering about the oxygen concentration's effects on the animals and diversity of life on land.
Okay, so to your first question, I work at a university, which means I can do independent work, not for the government. The money we get is indirectly funded from the government, but it's from a funding organization which received money from the government, but the funding organization is completely independent from the government. Very, very similar to the way it is in the US, where you have the National Science Foundation and places like that which give funding to scientists. So it's the same as the US. The second question, I'm not quite sure if I understand it, but I think, are you asking if decreasing oxygen will have an effect on life?
No, I mean that in your science departments, are they very small departments? Are they large departments? How many people in your group are working on these kinds of things? How many teams are working on these issues?
Pretty small. My group is about 6 people. It's very small. We don't get much money. That's another thing which I get frustrated about, because the climate skeptics say that, we're just saying all this to fund ourselves. If I wanted to make money, I'd be a businessman or a lawyer. I'm not doing this to make money. Okay, I'm smart enough to be something else if I wanted to make money, but I'm not, because that's not my interest. So it's a very small amount of money we get, both in our personal salary, but also in our research, and it's a constant battle to try to get more money. In terms of globally, to answer your question from the whole globe, the number of people that can make carbon dioxide measurements in the atmosphere in the whole world is only 200. It's a very small group.
And are these universities communicating with each other, sharing their data that they find?
Absolutely, yeah. We have meetings kind of every year, and then we get in trouble for flying to different parts of the world and burning CO2. But obviously we constant email contact, we write papers together. I still work very closely with Ralph Keeling in California by emailing, and we write papers together. So we all work very closely together. It's one nice thing about the job is it's a very nice, warm environment with everybody supporting each other.
Thank you very much for answering my questions. I appreciate it. Earlier, on one of your graphics, you were showing that where most of the heat comes in, the warming on the graphic, it showed that most of that heat energy was coming from the areas of land or areas of the ocean. So are we now looking at some of the changes in ocean currents as a result of that warming now?
Yes, we are trying to do that. If I can perhaps take that opportunity to mention something a little bit different. You might have seen the movie The Day After Tomorrow, where the east coast of America and Europe completely froze. The science of that movie was actually very good. They only got, let me tell you what the science was. Right now, Europe is much warmer than it should be because of an ocean current that takes water from the equatorial region of the Atlantic up to Europe. So northern Europe is very warm because of this ocean current. So what people are afraid of is if that ocean current slows down or stops, Europe could become much, much colder. And this has happened in the past, in the ancient past. And there are computer models which say if you increase CO2 3 times, that current will stop, which is ironic because it means global warming from more CO2 could actually make Europe much colder. It's another example where it doesn't, if some places are getting colder, it doesn't necessarily mean that global warming is not happening because of those ocean currents. So going back to the movie, The Day After Tomorrow, there's only one thing wrong in that movie, which is how fast it happened. But they got the science right. It's just instead of happening in a few weeks or months, it would have taken place in a few decades, which is still extremely fast and probably faster than humans could have adapted to. So yeah, but I've got colleagues at the university who are going in on ships, on research ships, and measuring the ocean current. There are people measuring that current, the Gulf Stream current. There are people with measurements in the ocean, checking the speed of that to see if it changes.
Thank you. I think in the interest of time, we're going to have to stop the public questions, but I believe we'll have some opportunity for questions privately after this. At this point, though, I would like to thank you, Dr. Manning, for coming and speaking to us today. And we have a small token of our appreciation for your presentation and being with us today. And I'd like to introduce Dr. Regina Olsen-Hughes, an alum of Gallaudet, and who has taught in our history department on World War I, but now is teaching in a number of different subject areas right now. And in fact, there is this is a piece of artwork that is done in her honor, and because of its connection to climate and the Earth as a whole, we would like to present it to you. Thank you. Okay, so this piece is named after her. Thank you very much. And I'd like to share with you now a proverb. Only when the last tree has been cut down, only when the last river has been poisoned, only when the last fish has been eaten, only then will you find that money cannot be eaten. This is an old Cree Indian prophecy, so with that, I bid you a good evening, and thank you very much.